How's it going, ladies and gentlemen? Mr. Donahue here once again. This time we're going to take a look at predicting the direction of reaction. So objectives will be to use the KQ value and expression to determine which direction a system will proceed in order to reach equilibrium given initial conditions. Or, if you want to put it simply, KQ versus Q. And we'll get into what those mean right now. So KQ versus Q. So we know KQ is the equilibrium constant. Its value represents the conditions of a system at equilibrium. So KQ generically is kind of like the products over the reactants to whatever power they need to be. So Q is the reaction quotient, and it's similar but different. So you use the KQ expression, but you put in your non-equilibrium conditions. So you'd plug in whatever values for pressure or concentration into the KQ expression, and you get a number. This is Q. Now you can use Q and compare it to KQ to see which direction the reaction will proceed. So if Q is greater than KQ, that tells us we have too many products and the reaction will proceed to the left, making more reactants. If Q is less than KQ, it tells us we have too many reactants and the reaction will proceed to the right, making more products. If Q equals KQ, then you're at equilibrium. You're there. So visualizing it. So if I have this simple equilibrium of X making Y, and, that I found a KQ value of 1/3 or 0.3. For every one product, I have 3 reactants. The equilibrium doesn't matter how much stuff you're working with. It's going to give you the ratio. So if we have small quantities, if we're starting with small amount, it's still this 1:3 ratio. If we use large quantities, it's still a 1:3 ratio. We're going to have this KQ be the same regardless of how much stuff we're using. So it's always the same proportion at equilibrium. So let's talk about Q versus KQ. So the reaction quotient is used to determine which direction the reaction will proceed in order to reach equilibrium. It's the KQ expression with initial values plugged in. So same equilibrium that I was using a second ago. A reaction vessel is charged with 1 atmosphere of X and 1 atmosphere of Y. Predict which direction the reaction will proceed. Alright, so if I were to visualize Q, it's a 1-to-1 ratio, or 50-50. So you can tell right now that, hey, this is not the same thing as my KQ. I have way too many products. So what's going to happen? Well, because our Q is equal to 1, right? It's the KQ expression, but with our values plugged in. That tells me that, hey, my Q is bigger than my KQ. I have too many products. So what's going to happen? Well, the reaction is going to proceed to the left, so that it makes more X. So we're going to convert some of these products into reactants. We're going to favor the reverse reaction. All right, what about the same equilibrium but different setup? So a reaction vessel is charged with 4 atmospheres of X and 1 atmosphere of Y. So now it's a 1-to-4 ratio. All right, if I plug in my Q, it's going to give me 0.25. Now Q is less than KQ. You can see visually that I don't have enough products in my initial setup. So I'm going to have to use up some of those reactants and make more products. So KQ is telling me that, hey, I'm going to have to proceed to the right to make more products. So here's another generic one, right? What direction will the equilibrium proceed if a reaction vessel is charged with 3 atmospheres of Z, 1 atmosphere of X, and 1 atmosphere of Y, and they tell me the KQ value is 10. So let me first figure out what my KQ expression is going to be. It's going to be the pressure of Z divided by the pressure of X times the pressure of Y. So let me plug in the values they gave me. All right, 3 atmospheres of Z, 1 atmosphere of X, and 1 atmosphere of Y. That's going to give me a value of 3, right? So my Q is equal to 3. 3 is much less than 10, so I'm going to have to shift to make more products. Which means I'm going to shift to the right. Because my Q is smaller than my KQ, it's telling me I don't have enough products. I need more products. I'm going to have to make more products. What direction will the equilibrium proceed if a reaction vessel is charged with 20 atmospheres of Z, 0.5 atmospheres of X, and 2 atmospheres of Y? So same process. Figure out what my KQ expression is going to be. Well, it's going to be pressure of Z over the pressure of X times the pressure of Y. So I plug and chug now. 20 atmospheres of Z divided by 0.5 atmospheres of X times 2 atmospheres of Y. I'm going to get 20 as my Q. All right, well, how's that compare to 10? Well, it's bigger. So if Q is greater than KEQ, it's going to have to shift to the left. It's going to have to use up all that excess product to make some more reactant. What direction will equilibrium proceed if reaction vessel is charged with 20 atmospheres of Z, 0.5 atmospheres of X, and 4 atmospheres of Y? Well, same process, right? So my KEQ expression has remained unchanged from the other examples. So I plug and chug 20 atmospheres of Z over 0.5 atmospheres of X times 4 atmospheres of Y, and that's going to give me 10. I am at equilibrium here. It's not going to shift in any direction because it's already at equilibrium. So Q versus KEQ, to summarize, if it's Q is equal to KEQ, system's at equilibrium. If Q is greater than KEQ, you got too much product. Reaction will proceed to the left, making reactants. And if Q is less than KEQ, too much reactant, reaction proceeds to the right, making more products. Right? So here is a real example with all the ugly elements and stuff plugged in. So at 500 K, the equilibrium constant for this reaction is 6.5. A closed container at 500 K has added to it 3 atmospheres of bromine gas, 1.5 atmospheres of chlorine gas, and 1.7 atmospheres of BrCl gas. Based on these initial conditions, what will happen inside of the container? So again, figure out the equilibrium expression. All right, so it's going to be the pressure of BrCl, but that's going to get squared all over the pressure of Br2 times the pressure of Cl2. So now I plug in my values. All right, they tell me BrCl is 1.7. So I'm going to have 1.7 squared all over, let's see, 3 atmospheres of bromine. So 3 times 1.5 of chlorine, which is going to give me, I cheated, I wrote stuff down. I got 0.642. So that's my Q is significantly less than my KEQ. So I'm going to have to shift to the right. It's saying I don't have enough products, so it's going to shift to the right to make more products using up some of those reactants. So summarize. How to use KEQ value and expression to determine which direction a system will proceed in order to reach equilibrium given initial conditions. So KEQ versus Q. I hope you found that helpful. Okay, bye.